Okay, now let's say we got a 0.8 meter high and 1.5 meter wide glass window with a thickness of 8 millimeter. So 0.8 and 1.5, that will give us an area which is here. Area is 0.8 times 1.5. The thickness is 8 millimeter, which means this length from here to here, this is 8 millimeter. Now 8 millimeter, I need to convert into meters. So 8 times 10 to the minus 3. Then the value of the K, the thermal conductivity, is 0.78 watts per meter. So I got thermal conductivity 0.78 watts per meter Kelvin. Find the steady rate of heat transfer Q dot is to be found through this glass window, and the temperature of its inner surface for a day during which the room is maintained is 20. So the inside temperature here is 20, the outside temperature is minus 10. So the difference is going to be 30. Now the value of the H1, take the heat transfer coefficient on the inner is 10. Inner is 10 watts per meter square centigrade, and the outer is 40 watts per meter square centigrade. And this includes the effect of radiation. If not, we have to assume, yeah, the radiation is included. So if I just show you the diagram, if I zoom that one in, let's zoom that one out. It is a good idea to actually sketch the diagram. So that's the inner temperature 20, the outer temperature minus 10. Hence I got the temperature difference of 30. Inside, the value of the heat coefficient is 10 watts per meter square centigrade. Outside, it's 40 watts per meter square centigrade. The L, which is the thickness of this window, is 8 millimeter. And we have the inner and outer temperature. Okay. So let's proceed to this question. Okay, now first we need to make some assumptions. The heat transfer to the window is steady. We need to make that assumption. It's a steady heat transfer. And we need to make sure that from a certain depth of the window, the L, the temperature remain constant at the specific value. So these assumptions need to be cleared, need to be mentioned. Excuse me. The heat transfer to the wall is one dimension. It is not going in other dimension as well, not along the y-axis, since any significant temperature gradient exists in the direction from the indoor to outdoor. So, or you can just simply write it's a one-dimensional heat transfer. Thermal conductivity is constant, which means the wall or the glass is dry. There is no water molecule. There is no foreign bodies in it. The thermal conductivity is given, which is 0.7 watts per meter Kelvin. Now we need to find that one. Now on one side, the inside, there will be convection, and then inside the glass there will be a conduction. So we need to add the R total. We need to find the R total. First we find the area, which is 0.8 times 1.5, which will give you 1.2 meters squared. Then we need to find the individual resistance. Now you know the resistance for the convection, it's 1 over H1A. Now 1 is 1, H1 is 10, and A is 1.2 meters. Where we got the A? We got the A from finding the area, 0.8 times 1.5. And that will give you a value. Make sure when you record the value, record it to multiple decimal places, because a tiny bit of this one can have a massive effect. So at least go to 4 or 5 decimal places for the value of the R. Now because for the glass, the R is a solid. For the glass, the R is a solid. So it's L over Ka, where L is the thickness. That was 8 millimeter. So we need to convert that into meter, 0.008. K is given, which is the thermal conductivity, which is 0.78. That's the K. And the area will remain the same, 1.2. Make sure that's in meter, standard units. And we will get a value for the R of the glass. Once we got the value for the R for the glass, we need to find the R for the outer side. Now outer side of the window, another convection happening. So I got 1, we use the convection R formula, 1 over H2A. 1 is 1. H2 for the outer is 40. And the area for the outer is same area, 1.2. So now we got the three values for the R. The first value here, that's our first value. The second value for the glass, the conduction, and then another convection we got here. Now we need to, because they are in series, we need to add all these resistance and we will get the total resistance. So the first resistance is because of convection, the second resistance is because of the conduction, the third resistance is because of the convection again. When you add 0.08 plus 0.008 plus 0.02, you will get an answer. Make sure you write that at least 4 or 5 decimal places, because a tiny value of the R will have a major effect on the Q value. Okay. Now, because then the heat rate is steady, we will use a heat transfer formula. We will use the formula. It is T1, T infinity 1 minus T infinity 2, where T infinity 1 was the inside temperature and T infinity 2 is the outside temperature of the surrounding. Yeah, not in the wall, not inside the glass. Yeah, it's inside the glass and outside the glass, not of the glass. So because we find the T total, so that temperature inside the house is 20 and outside the house is minus 10. So 20 minus 10, that will give you 30, and the R total is 0.112, and that will give you, if you put that on, the heat transfer will be 266 joules per second, which is joules per second is actually a watt. So we write joules per second is watt, which means every second you are losing 266 joules of energy. Okay, now we got the value for the steady rate of heat transfer, which was 266 watts. Now the question is asking you to find out what is the temperature here, temperature of the inside of the glass window, T1, and that's what we need to find out. Now to do that one, we have a formula. Q dot is equal to T infinity 1, because the inside temperature of the room, you can change it from 20, 30, 40, and T1, which is the temperature of the inside of the window, over the R convection, because the first step is only the convections happening. So I'm just going to take that value. So I need to rearrange the equation. This is given 266. So I put the 266 here. This convection can go on the other side. Yeah. So if I do the steps here, so what will actually happen is it will become a Q dot multiply by R convection 1 equals T infinity 1 minus T1, and this T1 is the one I'm trying to find out. So I can move the T1 here and that thing here. So that will become a T1 equals to T infinity 1, that's the one, sorry, minus Q R convection 1. And we put the value. T infinity 1 is 20 degree, that's a 20 degree, minus Q is 266 from here, and R convection 1 is that value, whatever this value was, 0.08333, and we put that one. That will give us the value for the temperature T1. So which means if that was a window, the temperature of inside of the window is negative 2.2 degrees centigrade, even though the temperature of the window is 20, of the room is 20 degree. Inside, the window will be a lot cooler. If an outside one will have the same temperature as the surrounding, a little bit different. It might be minus, because outside minus 10. So in this case, the outside we can find, if you want to, it will be around either 10 or 9, minus 9. So very close to the outer temperature. Okay, that's it.